we now have an exciting talk by Thiago this here on all I was told is something cool about quantum simulation. So I think, and I checked with Thiago and he said this is an accurate description of his talk, so we can judge that for ourselves. So,
great. Thank you for having me. Let me just make sure I have the time. So today I'll be talking about fast mixing in all-to-all quantum systems at high temperatures. And this is based on this new preprint and also some prior work with Anthony where we develop a lot of the techniques, and I'll be talking about that too. So the broad outline for today is to start by setting up the stage, talking about some background on Hamiltonians and Gibbs states and Markov chains. I'll talk about the results. I'll kind of explain next the main kind of technical new ideas. And the remainder of the talk will be more conceptual, talking about classical and quantum simulation of these systems with an outlook towards open problems. So upon suggestion, I was told to add emojis about where to follow this talk. So broadly speaking, the third point of this talk will be a lot more technical, and it's meant to be a bit of a tutorial on how to use some of these ideas. So feel free to nap if that's not of your interest. But the last part will be a lot more interesting. It'll be more conceptual, less math. Great. So today we'll be talking a lot about local Hamiltonians. And I've pictured here perhaps the simplest family of local Hamiltonians, which are one-dimensional quantum systems. So here you imagine you have an array of n qubits where the qubits interact with their neighbors, and each interaction is captured. Each interaction is captured by a 2x2 matrix, or over qubits, 2 to the q by 2 to the q matrix, a Hermitian matrix. More generally, we'll be talking about arbitrary all-to-all k local Hamiltonians. Here I've pictured a 2 local Hamiltonians, so a graph, where just to enforce normalization, the interaction strength per edge is 1 over the maximum degree. Great. So the goal of the talk is to prepare their thermal states. So this here is the Gibbs state. It's the matrix exponential of a Hamiltonian for a given fixed inverse temperature beta. And if this is the first you see this, then an instructive sanity check is to take the beta equals 0 limit, where you just get identity. So at infinite temperature, you have maximally mixed states. Great. So what's the prior on what we should expect to be able to do in thermal state preparation? Well, the big picture is that, at high enough temperatures, you kind of approach the maximally mixed state, and you expect that, measurements on, measurements on a given region, say A of the qubits, shouldn't really affect measurements on a faraway region C of the qubits, as the temperature is high enough. So this is captured by decay of correlation properties. What's rather remarkable about 1D systems, and why I isolated them at the top, is you actually have this decay of correlation property at all temperatures. So this was originally proven in 1969 by Araki, and the mechanism for which I'll kind of comment more on shortly. Are there any questions about the setup? Yeah?
By all-to-all, you just mean you're not imposing it. Not like every qubit interacts with every qubit.
Yeah, there's no geometry. It could be a dense graph. It could also be like a sparse graph, which is an expander. Just no constraints. The important point is that the constraints are balanced. They're just 1 over the degree. Okay. Also, this is meant to be somewhat interactive. If you have any questions, feel free to interrupt and ask questions. Good. So.
Sorry, what do you see on the horizon? Zero temperature. Are you talking about gapless or?
Right. So nothing except for the interactions being balanced. So 1 over the degree. So this will be about thermal state preparation, not ground state preparation. But I'll make the limitations of the techniques clear in a second.
So I'm sorry. So are you claiming that these Hamiltonians are not really hard?
I'm not claiming anything. It's just a definition. These are the families we'll be considering. There are such families which are QMA hard to prepare their ground states.
But is this true also for 0 temperature?
No, it will only hold at finite temperature. Okay, good. So again, we're trying to prepare their Gibbs states. And the way we're going to do that is in the modern Gibbs sampling paradigm, where the goal, broadly speaking, is to study their rate of thermalization. So as they approach the Gibbs state when coupled to a thermal bath. So this is rather physics jargon, but really what it means is that we'll be running a quantum algorithm, which looks very much like a quantum Markov chain in some sense, in the precise sense that the time derivative of a given state is given by this linear superoperator, L, called a Lindbladian. It's just a linear map. It acts by right and left multiplication. But what's important is that it's local, in the sense that it's a sum over local terms, and it's detailed balanced, meaning it will eventually converge to the Gibbs state. Okay? So given, much like classical Markov chain Monte Carlo methods, these algorithms will succeed eventually, and the question is how long it takes for them to succeed. And the rate of convergence of these Markov chains can essentially be captured by an estimate on their spectral gap, which is the main theme of these works.
And Thiago, just to be clear, it's like converging to the steady state, not just for L overall, but for each also, right? Is that right?
Right, so just a single jump may not be ergodic, but at the very least, the Gibbs state is the fixed point of each update.
Oh, okay.
Okay.
But are you assuming ergodicity in general?
Yes, yeah. Okay. Good, so we want to compute these spectral gaps. So with that, what are the results? So the first result, and the one in this new paper, is a mixing time estimate for these all-to-all systems at high temperatures. So the following statement will be a little technical, but I'll try to unpack it in words, which is, for any such k-local Hamiltonian of a bounded degree d, there's some critical temperature above which the Gibbs sampler is gapped, and in particular has a system size independent spectral gap. So independent of the number n of qubits as you maintain the locality k. So that's the technical statement. Now just a comment on what could you possibly expect. Following the normalization in the first slide, I'd recommend you think about two local Hamiltonians, so just a graph, where the interaction strength J is just 1 over d, so d times J cancels out. It's phrased this way for the generalizations, but really just think about J being 1 over d. Yeah?
Is this also normalized where the Hamiltonian terms are each less than or equal to 1 in norm, or 1 over d in norm?
J.
G. Oh,
Yep.
I see.
Okay. Good. So Q is the local dimension. 2 to the Q is the local dimension. Just think of it as a constant. And K is the locality.
And while we're at it,
Yep.
D and J.
Okay. So let's just comment on optimality. The dependence on the degree is optimal by the hardness of approximate counting. And that's kind of the main innovation of this work, improving the dependence on the degree. The dependence on K is not. In particular, both Alex and Bobak have told me that in locations these arguments can be improved, but it does seem quite challenging to push it to like polynomial in K, for instance. Good. So that's the result for all-to-all systems. The result for 1D systems in this previous paper with Anthony is very simple to state. Every 1D system admits a Gibbs sampler with a spectral gap that depends just on the temperature. So at all temperatures, at all finite temperatures, there's some system size independent spectral gap. Cool? Now, in terms of quantum algorithms for Gibbs state preparation, a spectral gap for the dynamics kind of already implies efficient, polynomial time quantum algorithm or quantum circuit for preparing the Gibbs state up to some accuracy. But a lot of the interest in studying these techniques is that they also give rise to very nice applications in terms of algorithms and structure for Gibbs states. So that's what I'll talk about next. The first thing for all-to-all systems is an algorithm for partition function estimation. So what this entails is, again, in the same setup and context of the first theorem, bounded degree, bounded interaction strength, finite temperature, or high temperatures. there's a fully polynomial time quantum approximation scheme for computing partition functions up to some relative error. I can go on about the motivation for computing partition functions. There's connections to statistical physics and approximate counting. I won't go into too much detail about that here, but you're welcome to read the paper. What's interesting about this statement is that, to the extent of my knowledge, existing classical algorithms for the same task seem to take quasi-polynomial time. Now, I'd like to emphasize that I am not claiming any form of quantum advantage here. It is my understanding that you could perhaps refine the analyses in these algorithms to get polynomial time. It's just not claimed in those papers. Cool. And arguably, it's just quite nice that it's just an immediate corollary of proving the spectral gap. Good. Yeah.
Those the degrees fixed are polynomial time.
Yeah, so you should imagine the degree being like growing with n. So like a dense graph or yeah. Good. So what's next is circuit complexity, and the remaining applications will be for 1D systems. So yeah. It should be squared, I think, or maybe cubed. Yeah. 1 over epsilon squared, and then n to the third, I want to say. Maybe if you really squeeze it, it could be linear, but I'm not going to claim anything. OK. Good. So in terms of circuits, the remaining applications will be for 1D systems. And the claim is that, again, as a corollary of the spectral gap, every one-dimensional spin chain Hamiltonian admits a polylog n depth circuit. And just captured by the picture. And arguably, the reason that this is interesting is, previous approaches to the same exact problem on the complexity of circuit descriptions for 1D Gibbs states required linear depth, it seemed, either using a matrix product description or what's known as a patching algorithm. Cool. The final and third application is on new structural characterizations for 1D Gibbs states. So in particular, we claim that, again, as a consequence of the spectral gap, for any fixed inverse temperature beta, the Gibbs state of a quantum spin chain satisfies an exponential decay of 2-point correlation functions. So now I can add a formula to the picture I had before. It's arguably very simple to describe. You kind of measure these two operators x and y, and you compare them to measuring them separately. And that correlation, or variance, decays exponentially with the distance. And the reason that this is pretty interesting is that it generalizes this kind of famous statement from 1969 by Araki, which was for translationally invariant systems, to finite non-translationally invariant systems. And kind of the key idea, or one of the key tools we use, is to kind of bootstrap a sub-exponential decay, proved recently last year by, yeah, 1D. Yeah.
The last two, right?
Yes, both of them are for 1D.
Just the middle theorem. What is the scaling of CQ beta?
Yeah, that's a fantastic question. So I will say the polylog n is just squared. It's log squared. Could potentially improve to like log than many trailing log factors. CQ, I will probably figure out for a journal submission what the dependence on beta is. It seems to be like quadruply exponential in beta. Yeah, not ideal.
So I should think of this then as imaginary time evolution for time beta.
That's a good point. So imaginary time evolution does appear, like that's y, but then we pay exponential factors in that locality twice. Yeah.
Do you know off the top of your head, like the comparison between your result and the previous NPO type results in terms of dependence on beta? Are those also done with exponential beta?
So the previous MPO results, given that they end up having like a larger circuit depth description, the dependence on beta tends to be much better. There are results with just singly exponential dependence on beta, There may even be some with like polynomial dependence on beta. I should also point out the both Ainesh and Sam, who are at this workshop this week, have some new results on 1D systems as well, kind of building on these statements, improving the MPO bond dimension. Good. Okay, so with that, let me kind of briefly discuss prior work. Actually, we'll spend not a brief amount of time. I'll spend a significant amount of time kind of surveying how the prior arguments work, mostly because I think we have the benefit of standing on the shoulders of giants to come up with these arguments. Yeah.
About the second theorem that you had before, this is an implication, direct implication of the previous
Of the spectral gap.
right?
Yeah. Yeah. I'll comment more on it in a bit. Yeah.
Is that, in the comparisons to the MPO stuff, those require also a gap in the spectrum, or
Not in 1D. I don't think so.
not?
No. Okay. Good. So there's a rich and maturing literature on computing spectral gaps for detailed balanced quantum Markov chains, and I wanted to survey a little bit of it. So starting with this very nice work by Michael Castoriano and Fernando Brandão in 2016, there's been a rich literature studying mixing times for commuting lattice Hamiltonians, and broadly those are based on decay of correlation assumptions. Now, what's kind of quite intriguing about this literature is that there's no one universal notion of decay of correlations. Even if the Gibbs state is commuting, kind of as we'll see soon, notions of inner products will not be commuting, and as a consequence, everyone has their favorite definition of decay of correlations, which implies mixing. There's been several works on studying stabilizer models, but I won't really comment on that right now. What I'll focus on is, starting with this work of Rouzet, Franza, and Alhambra, there's been a recent spur of studying mixing times for non-commuting systems, in particular on lattice Hamiltonians, largely based on kind of influence conditions or Dobrushkin-style assumptions, which I'll kind of comment on in a bit. And this is in part the conditions we use in this recent paper. But what I'd like you to focus on is that by and large, all the works on this slide only work for lattice Hamiltonians. And that's the gap that I'm trying to close in this new paper. Yeah.
The noise model, basically you have a Hamiltonian plus some noise. You assume that it's local, or you assume it's decaying, or what do you say?
Right. So the Lindbladian dynamics, as I'll comment on briefly, it is quasi-local. So even if the Hamiltonian is strictly local, there'll be an exponentially decaying tail to like the updates. I'll make this precise in a short while. Okay. Good. So finally, of course, there's many results just directly approaching the applications on the previous slide. I'll refer you to the paper to kind of a survey of that literature. So in the next few slides, I kind of wanted to comment on the structure of this Markov chain in a bit more detail and how the arguments work at the high level. And this is where the math part kind of starts. Good. So broadly speaking, if we were talking about classical Markov chains, you would expect a dynamics something like this, where you have a probability vector. The time derivative of the probability vector is governed by a Laplacian, which is also a sum over local terms, and it fixes some stationary Gibbs distribution pi. Much like this classical dynamics, we have a quantum dynamics, where now the states are density matrices. The changes to those density matrices are linear operators, so right and left multiplication, and they fix the Gibbs state. So in the classical setting, the updates are relatively simple to describe. They're just bit flips. In the quantum setting, we do need to change a little bit the structure of the dynamics in the sense that each update in this family of quantum Markov chains will be the time evolution of a bit or an X or Z operator. And the time evolution is filtered by a Gaussian filter, which depends on the temperature. So this Gaussian filter was arguably the key insight in this arguably seminal work by CKG, in which it plays a key role in ensuring that the updates are efficiently computable and that they're quasi-local, in the sense that you only need to simulate for a short amount of time, and the short amount of time ensures quasi-locality. So there's an exponentially decaying tail with the distance. And I'll make this quasi-locality precise in the next slide. The actual structure of the dynamics is highly explicit. It's also extremely scary to look at. But it is important to write it down at least once because it will be reappearing later. The important part of this formula is that you have this type of Krauss-like operator. And since it's continuous time, you want to ensure it's trace preserving, so you subtract by a symmetrized amount. Don't worry too much about the structure of the dynamics. What's important is that the Krauss operators, the updates, are these time evolutions. Good. So just as a sanity check, what happens when you take beta equals 0, so the infinite temperature case? The time evolution just completely localizes. You simulate for 0 time, so it's just A, and you end up getting the depolarizing channel. So this is stemming from the intuition that if you run the infinite temperature dynamics, the Gibbs state is the maximally mixed state. You're just running the depolarizing channel. Good. So with that, how do these proofs generally work? The big picture, or at the very least the starting point, is to first think about a mechanism to quantify how information percolates throughout the system. So the idea is that at the very least on lattices, Lieb-Robinson bounds enable us or give us a mechanism to express or quantify this percolation, where the math picture is that, let's say we're simulating a local operator A for time t, and we're going to compare it to the same time evolution where we truncate the Hamiltonian to a distance L around the operator. And the claim is that this truncation to the time evolution is accurate to an exponentially decaying error in the distance. Okay? That's all it's really saying. Some people call this a shell or annulus decomposition because you're writing the local operator as a sum over shells. Good. So what RFA, this initial paper on non-commuting systems, did was to observe that this just immediately gives quasi-locality properties for the dynamics. In particular, the dynamics, the Markov chain updates, much like the time evolutions, also satisfy this form of locality, exponentially decaying in distance. But furthermore, they satisfy a locality in temperature, where...
What is LA L plus 1? Does it include also LA L, or is it only...
Yeah,
It does include.
Yeah, it does. It's as if you were to literally take one update and truncate to distance L. Okay. The second point being locality in temperature, in that if you were to compare the dynamics at some fixed temperature beta and compare it to the depolarizing channel, that error also scales with beta. Yeah?
What's HL again?
HL are all the Hamiltonian terms at distance L from this Pauli operator A. So you have a Pauli operator A, and you consider the Hamiltonian terms just on the neighbors, or the neighbors' neighbors, and so on. Yep. Yeah, good. This is 1-to-1. What this means is that you input an arbitrary operator, a fixed 1 norm, and you compute the 1 norm at the output. So if you have a channel or some linear operator, N, the P2P norm is the output versus the input. Cool. Good. So put together, what this is really saying is that the finite temperature case is just some perturbation of the infinite temperature case. And this ends up being kind of efficient to push through kind of a mature technology. In mixing times, there's actually from this point various ways you can conclude the proof. The first one was based on these kind of very nice ideas stemming from Hastings like 20 years ago, related to the literature on gapped ground states, which will make a reappearance at the end of the talk. Good.
What's the statement that you're proving exactly?
So right here, I'm just saying, look at these.
The whole.
So this isn't a complete proof, but really what it's trying to get at is that the gap of L is constant. And the idea is that the gap at 0 temperature is just the gap of the depolarizing channel, which is constant. And we're just perturbing the depolarizing channel. Okay. So this is how the original arguments worked. And the reason why they kind of don't capture the systems I'm studying today is for 2 reasons. So first of all, in all-to-all systems, like a dense graph, there's no notion of geometric locality to run this Lieb-Robinson bound over. So this first bullet point doesn't work. And in one-dimensional systems, we expect it to mix at all temperatures. So this locality and temperature condition is just useless or trivial, because you can imagine beta being equals to 5 or 10 or 100, and this 1-to-1 is just bounded by 1. So somehow we kind of need to re-engineer the proofs around these like initial locality estimates. Good. So that brings me to the second part of the talk on this new framework for proving mixing times. And I think potentially in the interest of time, I won't actually be talking about like how we structure that proof. I'll just present some definitions. But I do have slides on it, so please feel free to ask questions at the end if you want to know how an individual piece of the argument works. Good. So to begin, I wanted to set up with some basic definitions, remind you guys what we're trying to prove, and really try to serve as a bit of a tutorial on some of this type of mathematics. So again, what are we trying to do? We know that this dynamics, starting from an arbitrary initial state sigma, will converge to the Gibbs state rho. So again, the question is, how fast does it do so? So it's oftentimes instructive to instead consider what happens in the Heisenberg picture. So what happens if we were to run the adjoint of the dynamics on a generic operator x? And you can convince yourself that what happens is that it trivializes the operator x. It will drive it to identity with a scalar coefficient, which is just like the mean of that operator. A natural kind of potential function, then, is to quantify how far x is from the mean. So this is just the variance of x. And now this kind of sub-rho quantity here might seem a little weird. It's just a certain non-commutative inner product referred to as the KMS inner product. Now, if this is the first time you see this object, it's instructive to think about what would happen classically. So if you imagine x, y, and rho are just classical diagonal matrices, then it actually doesn't matter where you put the powers of rho, because they all commute. But in non-commuting systems, it starts to matter, and it turns out that the correct answer are these symmetrized powers of 1/2. Good. So I'll put that in the top right-hand corner. And we can now ask the question, we have this bona fide potential function, which is the variance. It quantifies how far we are from fixed. Let's start taking time derivatives of it. Yeah, there's a math mistake, which I only captured.
The measure is the Gibbs state.
Yeah, the measure is the Gibbs state, yeah. All these weighted inner products are weighted with respect to the Gibbs state. Yeah. Good, so potential function, let's take time derivatives of it. It should be ×2, sorry about that, but basically, this is a quadratic form. When you take derivatives of exponentials, the L tumbles over. You can convince yourself that this time derivative is just the inner product of x with itself, driven by L, the dynamics. And this inner product has such a plays such a central role that we give a special name to it. It's called the Dirichlet form. the crux of the spectral gap method is to say, if the Dirichlet form itself is bounded by the variance, then we get an exponential decay of the variance. So in particular, let's just look at this bottom formula. If the Dirichlet form with a negative sign is bounded by minus gamma times the variance, this is just a first order ODE, we get an exponential decay of the variance, where the constant is the spectral gap. Okay? Now, this is just some basic definitions. It's kind of, the role is to kind of get used to these non-commutative inner products. But given how central that we've seen the role of locality is to like the Lindbladian dynamics, perhaps a natural approach is to attempt to coarse grain or to kind of try to do some form of recursion over the gap. Kind of broadly inspired by classical proofs and this initial work for commuting systems by Fernando. So again, a natural approach is to attempt to recurse. Yeah, I'll make that precise in a second. The fundamental question here is, suppose you were to simply run the dynamics on a subregion R of the system. So here R are these two qubits in the middle. How long does that take to converge? That's the question. And the intuition is that surely if the dynamics was quick to mix on a patch, on two nearby patches, then intuition would hope that they're also quick to mix on the union of the patches. That's the broad vision. So let me move the question up there. So how do we quantify this? Well, we quantify it using a notion of a local gap. Much like how the variance captured the distance to the kernel, the local variance will capture the distance to some local kernel. So just to make this precise, we have the dynamics just localized on the region R, summing the updates on the region R. We can consider what happens when we run the dynamics forever on this region R. So that's this expectation operator. And the variance is just, again, the distance to this kernel. Yeah?
So why didn't we switch to this question of looking at the dynamics on the local region, or was that became clear later?
Yeah, I mean, the vision is that locality plays such a central role to the definitions of the dynamics and why it's efficiently implementable. One could hope that you could try to locally compute some gap and argue that it can be grown. So broadly speaking, classically, that's how a lot of classical mixing time proofs are, and we would hope to try to reproduce that here. Okay. So we've defined a local variance, and the local gap just captures, again, the rate of convergence of this local variance. So now that I've set up a lot of the definitions, the next two slides will be on a key concrete question which kind of motivates a lot of the technical work we've been doing over the past year, which is, what is the local dynamics even converging to? So if I tell you that I run these updates on a patch of 2 qubits and it's no longer doing anything, can I characterize structurally the fixed point that I've arrived at?
Is it even clear that it is convergent?
Yeah, that's a good point. We'll get to that in a second. Good. So the following formula will be a little scary, but it conveys some meaning, and we'll try to unpack it in the next few words, which is, Rouzet and Anthony, they derived an explicit formula for this local Dirichlet form, which sheds some form of light on what these fixed points are. So what this formula is capturing is, again, you run the dynamics on a single qubit I, and you look at the Dirichlet form, so the time derivative of x under this local update. And it looks like this very weird integral expression with some integral over frequency and time of these time-evolved operators, or the commutators of time-evolved operators. Now, this is kind of abstract, but the real takeaway here is that the kernel of a single update are the operators which commute with all time evolutions of local operators. Now, this is quite a dense statement, so I'm going to spend some intuition in the next few slides. But really what I'm trying to convey here is that there's been lots of recent technical effort which has led to developments in learning, learning theory and Markov properties, and also this 1D paper, to get around the simple fact that we do not know how to compute local gaps for the CKG Lindbladian, which would be a trivial task classically and in commuting systems. So, what's up?
Sorry, you said with some 1D paper?
Oh, the like hours with Anthony that I'm talking about. Okay, so it doesn't, this seems to be a really fundamental issue that we don't know how to locally characterize states that are stationary under local updates. And this seems to be quite like a fundamental quantum phenomena. Like in particular, under the CKG Lindbladian, you can imagine having a spin chain and you only update a single qubit at the boundary of the spin chain. It's entirely conceivable that that could mix the entire chain for a sufficiently non-commuting system. Now this is like mind-boggling classically, right? Like you would never have this classically. You have a spin chain where you just update a single bit. The others are fixed. They don't change. But for a sufficiently non-commuting system, in principle, a single update could mix the entire chain to the Gibbs state. And there is some evidence that this occurs in this very nice paper by Carlin on boundary-driven quantum systems. So in part, this is why characterizing the fixed or the local fixed points in the local kernel is so challenging. Good. So also I should comment that this is somewhat akin to like closed system thermalization, where you just run the Hamiltonian dynamics and you look at a subsystem. But that's more for the physics audience. So that kind of captures the key challenge here. It's really difficult to characterize these local kernels, and we do a lot of like heavy lifting to kind of work around this fact. Which brings me to a solution to this problem, or at least a partial solution. Yeah.
Can you say more about this? This is weird.
Yeah.
So you're saying, I mean, classically we could have, of course, something, local transitions that basically, I don't know, mix things, and then you just change a single point on the left and it propagates to the rest. So that's not what.
So I'm talking about like Glauber dynamics. So it's just a Markov chain with local updates where you like flip a bit conditioned on its neighbor. And you know, if you just update a single bit, there's no way for all the other bits to change. So classically, a like detailed balanced local Markov chain can never mix the entire system. Like it's not ergodic. There's no way for it to converge. But what I'm arguing here is that, like, since the updates in these like non-commuting Lindbladians are time evolutions, the time evolution spreads through the entire system. So in principle, it could converge the entire chain.
But Thiago, you could have a classical
Mm-hmm.
at one end. A Glauber updates just on one end.
And time evolution.
And a diagonal
Yeah.
commuting Hamiltonian, and that would be good.
Yeah, you need time evolution too.
Sure, but the generic system would be something like an Ising model with some path at one end. That's what you would mean by like a classical system coupled to a bath on one end does have a Hamiltonian.
Yeah, I guess I'm cheating then by saying like that the Markov chain is only dissipative. Yeah. Anyway, the punchline is that it's very difficult to characterize the local gap, and the counterexample are these boundary-driven dissipation systems or Markov chains. But that's a good point.
This is just a very elementary. What is Li again? Like, what is?
Oh yeah, it's like each like update takes a single Pauli operator, and it times evolves it and kind of applies it at some rate. And Li is like you run X, Y, and Z on a single qubit.
But Li itself is not like it acts on all the qubits non-trivially, or.
Yeah, it acts on all qubits non-trivially. Yeah. Okay, how am I doing on time? Okay, so good. So with that, the entire insight is to observe that we cannot characterize, this locally characterize the fixed points of the local dynamics, and kind of replace it by a strictly more localized dynamics. So what we'd like is instead a potential function which kind of quantifies how non-trivial an operator is at a single site instead of on many sites. So ideally, you'd like to engineer a dynamics which admits this commutator as the Dirichlet form. Because if so, we'd essentially be saying that the time derivatives are just governed by the commutators at a single site. So credit where it's due, what Anthony did was basically to reverse engineer a choice of Lindbladian, or essentially a Lindbladian, which admits this Dirichlet form. Now, this is quite cute, and it admits a series of very nice properties, very much akin to the original Lindbladian dynamics CKG. In particular, it's detailed balanced, which I haven't explained too much about, but for all intents and purposes just means that it fixes the identity, or the adjoint fixes the Gibbs state. It's negative semi-definite, and this you can just immediately see from this formula. In particular, quadratic forms are strictly positive, so K must be negative semi-definite. And crucially, it fixes the identity. So in particular, if you have an observable X, which is the kernel of these local updates, that means it must be trivial on that qubit I. So now we have an explicit local characterization of the kernel of this new dynamics. The only caveat, you might be asking the question, if we like this object so much, why don't we run this on a quantum computer instead of running CKG? And the answer is that it does not generate a completely positive and trace-preserving map. So in particular, it's not really a physical Lindbladian or channel that you can implement on a quantum computer. Thus, we either refer it to a pseudo or a spectral Lindbladian.
What's the statement exactly that given any Hamiltonian with local noise, basically, you can generate such a thing? Or what's the statement?
So here, this is just a mathematical object. It takes as input a Hamiltonian and a temperature, and a set of updates, which are just Pauli operators here. So A here.
But for any Hamiltonian.
Yeah, for any Hamiltonian and temperature, you can define this object. And it satisfies these properties. So it fixes the Gibbs state, it's negative semi-definite, and the adjoint fixes the Gibbs state, and it fixes the identity. So these two properties are also satisfied by the Lindbladian, the original one, but this one does not. Good. So this is arguably.
But it will have the same Gibbs. Convert to the same
Yes,
thing.
it will convert to the same thing. Right. So crucially, it does not generate a completely positive and trace-preserving map, so we can't physically implement it. And it's also the reason why the title of this paper is fast mixing and not to be confused with rapid mixing. So we only get a spectral gap, not a log Sobolev constant or a log n mixing time. And the reason why is to talk about log Sobolev constants, you need a completely positive trace-preserving map. You need something that satisfies the data processing inequality, if you know what that is. Good. So I will very briefly comment on the outline of the proof. I won't say much about it, just comment on the key ingredients, because I want to get to the final part on simulation, because I think it's just more conceptually interesting. Good.
But if you cannot implement it, then how do you get the application?
Yeah. So again, this is what the object looks like. It has these nice properties. The intuition of what this statement is saying is kind of like if the observable is already in thermal equilibrium at a site I, then updates on I won't spread any disagreements around the system. And this kind of idea of how you propagate disagreements is crucial to these influence type proofs of mixing times. So now, what's the outline of the rest of the argument? The first idea is, these updates, they kind of depend on what happens when you conjugate a Pauli operator by functions of the Gibbs state. And we have pretty mature tools for understanding how these objects behave in the form of cluster expansions. So cluster expansions kind of generically converge at high temperatures. They also unconditionally converge in 1D systems. And what this tells us is that we can kind of have good control over the quasi-locality of this object. Now, this is really technical and abstract, but really it's captured by the following question. Suppose you consider the complex time evolution of a local Pauli operator. So here, Z is complex. It's small. It's bounded by beta in absolute value. And you consider the complex time evolution. Is this a quasi-local operator? So cluster expansions allow us to answer this question. And I have some pictures about it, but I won't be showing you right now. Also, if you want some further details, Anthony has a nice talk on this at IPAM. The second idea is that once we have these kind of key quasi-locality properties for the Lombardian generator, these naturally feed into sufficient conditions for a spectral gap in the form of influence conditions or spectral gap recursions. I'm not going to comment too much about it, but at the very least, as I mentioned, largely based on recursion or Dubrushkin style conditions. Ewan has a fantastic talk about this on her recent talk on her recent paper at IPAM. I'd recommend you see her talk because she explains it much better than I could. Finally, to answer Dorit's question, the last step of the argument is to say, look, this new Lombardian is not physically implementable. Can we argue that a spectral gap for this object can be lifted into a spectral gap for the original dynamics? And the way this is done is by comparing their Dirichlet forms in PSD order. So this is what one would refer to as the Dirichlet form comparison argument. The kind of key idea is that we're trying to simulate the updates of L using the updates of K. And the conclusion is that the time derivative of operators X under K is strictly slower than the time derivative under L. So if we establish that K is gapped, then so is L. That's
probably not, if and only if you know examples.
It's somewhat challenging to show the converse sometimes. Yeah, but we can comment on that offline. Okay, good. So in the remaining 10-ish minutes, maybe, I will try to provide some discussion on outlook on quantum and classical simulation in the fast mixing regime, which are this spectral gap regime. And what I'll try to convey to you in the next few slides, the following slides hold for generic lattice systems. They're not just one-dimensional systems. And what I'll convey to you is when a spectral gap for the Lombardian dynamics also implies a low-depth quantum circuit for the Gibbs state. And the claim is, suppose we could prove or argue that the Lombardian dynamics for some lattice Hamiltonian was gapped all the way from infinite temperature to some fixed finite temperature beta. So the way I picture this is that the system does not satisfy, or sorry, the system, does not admit a dynamical phase transition. So in particular, the gap is constant in this entire regime from 0 to beta. The claim is that then the Gibbs state admits a low depth circuit. So I'll try to explain how this argument works. I think it's largely underappreciated, even though it was already in kind of at some high level in CKG, the original paper, although we flesh out some of the details in this recent paper on one-dimensional systems. The starting point is, again, we have the local Hamiltonian. Here it's drawn in 1D, but it holds for arbitrary lattice systems. And the dynamics, which is this quasi-local operator. And the starting point to the argument is to purify the dynamics into a local Hamiltonian on a doubled Hilbert space. So this isn't really super fancy, although maybe if it's the first time you see it, it might warrant an equation. So the Lombardian dynamics, broadly speaking, acts by left and right multiplication. It's just a linear operator. And ultimately, you can always vectorize this linear operator into something that looks like a Hamiltonian on a doubled Hilbert space. Okay? So that's what this picture is doing. The two dots represent the doubled Hilbert space. What's cute about this picture is that if the dynamics is gapped from infinite temperature to the fixed finite beta, then these Hamiltonians, the purification of the dynamics, defines an adiabatic path of gapped Hamiltonians. So everywhere along this curve of Hamiltonians parameterized by temperature, they're gapped. This enables us to use kind of some fancy machinery from the study of gapped ground states. So in particular, this very nice paper by Bachmann et al., kind of stemming from Hastings' spectral flow, says that if you have a gapped path of local Hamiltonians, a gapped adiabatic path of local Hamiltonians, then you can connect their ground states using the time evolution of a local Hamiltonian itself, or in particular, a quasi-local Hamiltonian. So that's what this purple object is doing. It's slightly more spread out, which indicates that it's slightly less local, but it's still some quasi-local Hamiltonian. The crux and the missing step is now to argue that this time evolution can be done in polylogarithmic depth using this very nice paper by Hastings, Kothari, and Lowe on the simulation of the time evolution of lattice Hamiltonians. So put together, what we conclude is that if the dynamics is gapped, again, from infinite temperature to finite temperature, then the purification of the Gibbs state admits a polylog n depth circuit. So, yeah.
It's also a very bad question, maybe. But does this have anything to do with the spectral gap of the Hamiltonian itself? Is this condition related to?
No.
Doesn't imply it, or?
It's the spectral gap of the dynamics.
Okay.
The Hamiltonian itself could be gapless. Okay. So the reason that this is so powerful is that not only does it give us low depth circuits for these Gibbs states, but it unfortunately also gives us classical simulation algorithms. Now, as as a corollary of this low depth circuit statement, if the quantum system again does not admit a dynamical phase transition in this sense, then it also admits a quasi-polynomial time classical simulation algorithm for computing partition functions using light cone arguments. You can then, using standard counting to sampling reductions, also get computing partition functions, which is arguably one of the key applications of these Lindbladian dynamics algorithms. And using some more fancy machinery in the simulation of low-depth quantum circuits, you can also compute certain global product expectation values. Now, I think one should kind of critically eye these results because, in a sense, they're saying that some of the main applications of these new families of quantum Markov chains, at least in the regimes where they're most efficient, namely the fast mixing regime, also imply classical simulation algorithms. That's not to say that arbitrary applications of the fast mixing regime can be simulated. In particular, maybe you'd like to use the Gibbs state as an initial state for some dynamical experiment, or maybe you're interested in sampling or just computing global expectation values. But at the very least, for partition functions, these systems are classically simulable. Now, I'd like to pose as an open problem reducing these runtimes to strictly polynomial time. Currently, there's some key bottlenecks to performing these improvements. But it does seem like an intriguing question for future work. So with that, sorry for going a little bit over time, but I wanted to just pose some outlook and open problems. So to summarize, we have these new techniques for proofs of mixing times in non-commuting quantum systems. Although I kind of didn't really get into it, like I think that there's some really nice new ideas in these Dirichlet form comparison arguments that I mentioned briefly at the end, and in some upcoming work with Michael, Kevin, João, and Lynn, some of which are in the audience. We have a new paper coming out on the Heisenberg model. An intriguing question is, all this work is done for fast mixing, which entails like a polynomial mixing time. Can these results be lifted to get rapid mixing, which is polylogarithmic mixing time? Currently, this seems a little out of reach for non-commuting systems. As I mentioned, since we don't know how to get like completely positive trace-preserving maps with local gaps. But maybe 2 years ago, this very nice work by Capel and collaborators basically showed something along the lines of what one would like to try, where they argue that if a Davies generator is gapped, then it also admits a log Sobolev constant using similar recursion techniques. And that's kind of the blueprint of what one would try to reproduce. In terms of mixing times, there still remains some highly non-trivial open questions. My favorite one, and really the systems that I wanted to make work and didn't, are spin glasses. So these are disordered systems. And later today, Alex will be talking about some recent progress in designing classical algorithms for these systems, which is very cool. Taking a step back, I mean, even if you don't believe that proofs of mixing times give new quantum simulation algorithms, or if you don't believe that like perhaps these are genuine microscopic models of nature or just quantum simulation algorithms, they do nevertheless offer a really versatile new approach to proving structural properties for Gibbs states. So the example of which we saw today was the decay of correlations in 1D systems, which had been open for a while. But also, Anthony and Ewan, they have some very nice papers on proving Markov properties for Gibbs states, which was also open for a while and was proven using dynamical arguments. But the question that I find most interesting overall in this agenda is not at all what's perhaps left in the fast mixing, but instead what can be done in the slow mixing regime, essentially to ask the question of what can we prove in the absence of a spectral gap. And this is what we've been taking initial steps to try to characterize in this kind of paper on metastable quantum Markov chains, also with Anthony and Umesh. So with that, thank you very much for your time.
You mentioned that all you want to do is you want to move from lattices to non-lattices, and then nothing is meant right there.
Yeah.
Can you say a little bit more about it?
Yeah, so no. So the framework for the proof is the same in both papers. It is really like this flow. You have a generator. The starting point to any proof of a mixing time are quasi-locality properties. Once you have those properties, you put them into some sufficient conditions for a gap, and then you compare the spectral gaps. It's just that each of these steps requires new ideas in each paper. The first step is actually relatively simple to describe, so I'll picture it here. So how do we try to quantify some notion of locality in space for these all-to-all systems? It's the same question, and basically perhaps the simplest version of the argument is captured by the following figure, where you basically say, suppose you complex time evolve a single Pauli on a site, the blue site here. How much does that affect the second site? And the way that is done is by comparing the time evolution where all the Hamiltonian terms touching the second site have been plucked out. And you can answer these questions using cluster expansions. And in particular, I guess today is not Friday, but I'll comment a little bit on the usage of AI. So basically, what happened is I had some initial combinatorial proofs on these cluster expansions, maybe in January or something, while the models were not good enough. And then recently, I throw ChatGPT at them, and they kind of really simplified my proof to a point that like there's no way it could have been the AI model. Like the proof was now like 5 to 10 lines, which is quite concise. And after probing it for quite some time, I eventually like had it like produce the related literature, pointing me to this paper in 2004 by Natokny and Redig, who had already done the cluster expansion calculations. So the message here is I caution you guys in terms of using AI systems without providing credited sources, because they can sometimes produce new calculations which are not at all new. It's just hard to find in the literature. But anyway, this is a digression. The new idea is this.
And you also promised some like provocative questions. Did you not get to them, or did I miss?
Well, I think the provocative question is somewhat captured in this figure. I mean, ultimately, what we're saying here is that the entire fast mixing regime, at least for lattices, admits some pretty strong classical simulation algorithms. I think there's a valuable question to be raised in terms of, if you can classically simulate this quantum algorithm, would you ever run it on a quantum computer? The answer is probably not. I do agree that there's serious limitations to these classical simulation algorithms. I mean, they are quasi-polynomial time, but not polynomial time. Maybe that's not practical. Many quantum chemists advocate that there's potentially serious quantum advantages in the regime of polynomial speedups.
Or you don't?
Yeah, no. This argument works only for lattices, but it's entirely conceivable that one can redo some form of this program or like argument, where in particular the connectivity of phases argument. This holds for all-to-all systems. Yeah.
I also have a kind of question related to that on this slide, which is like, for this particular argument, does it also depend on the non-commutativity part, or is there some sort of like technical way you can get around that for like simulating
Sorry, what do you mean?
Oh, sorry. So my understanding is that like part of this like Hamiltonian simulation argument depends on the non-commutativity, or like how non-commutative or how far it is from being commutative. Is that important at all, or is there just like?
You mean HHKL?
Yeah.
So all HHKL uses is that the system satisfies the Lieb-Robinson bound. So in particular, arbitrary lattices. Surely it could be improved if like some of the terms are commuting, but.
You listed proving structural properties of open state. What are your favorite outstanding structural properties that are open?
Yeah, that's a good question. I mean, I think it's let's kind of take that question in two directions. One of them would be to try to prove some structural statement for spin glasses, potentially at high temperatures. There's various directions one could attempt to approach this, but I just don't think a lot is known in this regime. And the key bottleneck is that the random matrix theory is highly non-trivial, as you are well aware. The other direction is in terms of slow mixing. Very little is known in terms of characterizing quantum states which are approximately stationary. So that's what we call metastable under these Markov chains. New structural statements for these metastable states would be increasingly interesting if we believe that simulating them could be a viable and interesting quantum experiment to run. Yeah.
I think you're taking yours for SYK model.
SYK model. Yeah, that's a good question. I mean, the definitions are well posed. The challenge is captured by, I mean, there's a few challenges. The first and most fundamental challenge is answering this question for the SYK model or for a spin glass for that purpose. In particular, what can one establish in terms of quasi-locality properties for complex time evolutions of local Majorana operators in the SYK sense? It's also important that, I mean, we'll see some progress on this in Alex's talk later today, but the distinction from what he does and what we're doing here is that for mixing times, it seems that the notion of error is operator norm. Like you need an approximation in operator norm for like this complex time evolution, whereas for partition function, like zero freeness and other notions of operator growth, it's 2 norm, which is generally simpler to prove. Sorry. Yeah, sorry.
Okay, maybe this is a kind of soft question, but like, do you feel like out of systems that we care about in nature, are they typically fast mixing or is it slow mixing?
Yeah,
I
that's
don't know,
a good question. Generally, the answer is slow.
It's slow, okay. And that's like still viable as a place we can look for common advantage.
Potentially, yeah. But I think the important point to raise there is that in the absence of a spectral gap, potentially the naive approach, which is to just run the Markov chain, may not work. And it will be increasingly difficult to prove properties about. That's not to say that, you know, there's this whole agenda of, in the classical Markov chain literature, of having a warm start to your algorithm. Typically, you know, not all initial states are the worst case input states that will lead to slow mixing. You know, for various systems, trivial states are good warm starts. Yeah. It also should be said that all this is for, like these classical simulation algorithms are for the regime of constant gap. There's a few physical systems where the gap is inverse polynomial, which is still efficiently implementable on a quantum computer and yet cannot be simulated using these techniques. Yeah.
But you had some pretty general statements that guarantee such a constant rate.
At high temperatures, or in 1D systems. Yeah. I mean, the claim is whenever there is a constant spectral gap, then there's a low depth circuit.
And wouldn't it be true that if you below the critical temperature, if you restrict yourself to some sector, then the line is restricted to like a constant spectral gap?
Yeah, that's a fantastic question. It's not clear how these connectivity of phases arguments apply when you restrict the Lombardian. Any more questions?
Well, thanks, Thiago, again. And